Another common air handling process is mixing of two air streams. So in smaller air conditioning systems, a lot of times infiltration from the outside is what's used to provide fresh air for the space. So they know that there's enough cracks and door seals and windows and through the walls where people are going to have air to breathe. Because the surface area of, say, a residential house is pretty large compared to its volume. When you get bigger buildings that have more people in them, you have to supply fresh air to those people because the surface area to volume ratio goes way down and there's not as much cracks. And also, building codes are getting tighter where houses are going to need to be sealed even better. And so fresh air, even in a residential scale, might be an issue in the future. So a lot of times you'll have fresh air. So this would be like a wintertime scenario where we've got cold air outside. This is the same conditions that we did our heating problem with. We're going to take 300 meters cubed per minute of that and mix it with, this would be called recirculated air that came from inside the conditioned space. So imagine, like an air conditioner in your house, you've got probably in a hallway somewhere, you've got some air return. So that would be air that was taken out of the space that's already conditioned. And so that's what we have here. We're taking 25 degrees, 60% humidity air at 400 meters cubed per minute. We're going to mix those two things and create one airstream. And so really right now what we have here is we just want to characterize that airstream. We want to know its temperature and enthalpy and volume flow rate, relative humidity, and mass flow rate. So we want to go to the laws of thermodynamics in order to solve this. So first one we can use is the conservation of energy for this mixing chamber. Actually, let's start with the conservation of mass. That's the simplest. We've got mass flow rate 1 plus mass flow rate 2. Those are two things entering that system minus mass flow rate 3. And since this is steady flow, it's not accumulating or being depleted of any mass. That equals 0. This would be the rate of change of the mass in the system. Conservation of energy. The mass entering at 1 plus the mass entering at 2. Sorry, the energy entering at 2 with the mass minus the mass leaving at 3. That has to balance. And so we'll be able to find mass flow rates 1 and 2 from these two because these states are defined. We can get those specific volumes. With those and these volume flow rates, we'll be able to get the mass flow rate at either point. And then here we'll be able to get H1 and H2. From that, we can solve for enthalpy 3. So then we'll have this, and we'll have one thing that defines state 3. From the state postulate, we need another one. Our other thing that we can get at 3, I didn't ask it as a question, but we can get humidity ratio 3 because the conservation of mass of water also applies. So the moisture, the amount of flow rate of water entering at 1, so the flow rate of air times basically the concentration or the fraction of that is moisture entering at 1, plus the moisture that enters at 2, minus the moisture that leaves at 3, must balance. So conservation of mass, conservation of energy, conservation of mass of water, only the water portion here. So here we can get all those things, we'll know that. We can get humidity ratio 3, then we'll have two of these things, and then once we find that point on this chart, we'll be able to read anything else that we want. So let's do these. We want mass flow rate 1. The volume flow rate over the specific volume. Volume flow rate 1, 300 meters cubed per minute divided by the specific volume at 1. 4 degrees C, 80% relative humidity. Remember, that's the same point we had earlier. That looks like 0.79. And then 1 minute, 60 seconds. All right, mass flow rate 2. volume flow rate 2 over specific volume 2. We have a little bit more volume flow anyway at 2, divided by, let's see, state 2, 25 degrees, 60% relative humidity, 10, 20, 30, 40, 50, 60. So there is point 2. Whenever you mix two airstreams, the mix point is going to fall on a line in between them. You probably remember the lever rule from materials. So if, say, 90% of the mass came from 2, 0.3 would be over here. It'd be close to 2. Where if most of the mass came from 1, we'd be over here. If it was 50-50, it would be an equal distance. But here we're going to find, we'll actually solve for H3 and humidity ratio 3 and find that point, which just graphically it looks like we're going to have a little bit more mass coming from 2, and so it's going to be, roughly in this area. We'll see. All right, let's see. Specific volume at 2, it's just over 0.86, call it 0.861. All right, let's get these. .300 over 0.79 divided by 60. We've got 6.33 from here. $400,861. 7.74. Conservation of mass, we can get flow rate 3. .07. Okay. If we go ahead and solve for enthalpy 3, another way to think of this, enthalpy 3 is a mass weighted average of 1 and 2. So it's going to be, if I solve this for enthalpy 3, we'll get mass flow rate 1, H1, plus mass flow rate 2, H2, over mass flow rate 3. So it's essentially the mass fraction of 1 times its enthalpy, plus the mass fraction of 2 times its enthalpy. All right, mass flow rate 1, 6.33. Enthalpy 1, 14. And then mass flow rate 2, enthalpy 2. There's 50 and 60. I'm going to call that 56. All right, so here's enthalpy 3. 37.1. Kilojoules per kilogram. All right, let's do the same thing with humidity ratio. Find a piece of paper here. If we solve that conservation of mass of water equation for humidity ratio 3, that's what we get. Mass flow rate 1, 6.33. Humidity ratio 1. We looked it up earlier. 4 grams of water per kilogram of air, plus mass flow rate 2, 7.74, times humidity ratio 2, $12, divided by the total flow rate. $8.4. Okay, so if I go find the intersection of enthalpy 37, so see this line of wet bulb temperature is pretty much parallel to enthalpy of 37, so I'm going to draw that. Then humidity ratio 8.4. So here's 8, here's 8.5. So I'm just under this. So those intersect right there. So there's my mixed airstream. Notice it's pretty much on a straight line between 1 and 2. It's a little closer to 2 because more mass came from there. Okay. We can get anything else that we want there. So we wanted, let's see, the temperature. Looks like it's just over 15. We wanted, what else did we have? The enthalpy we already got. The relative humidity at 3. Here's 80, here's 70, so call it 77%. The humidity ratio at 3 we already got. The mass flow rate 3 we got. We don't have the volume flow rate, but we can use this again. Mass flow rate is volume flow rate over specific volume. So the volume flow rate isn't necessarily 300 meter cubed per minute plus 400 meters cubed per minute. There's no such thing as the conservation of volume equation, but we do have the conservation of mass, and we know the mass flow rate 3. We know specific volume 3, so we can get volume flow rate 3. Let's see if it's in fact 700 or not. We know the mass flow rate is 14.07. The specific volume at 3, there's 0.82, 0.83, called 0.828 meter cubed per kilogram. So I've got meters cubed per second. Let's multiply by 60 seconds in a minute to get meter cubed per minute. Let's see if it's 700. Since we didn't add or take away any heat, it's probably going to be close. Yeah, 699. Okay.